Very good morning and very warm welcome, students and teachers of schools. Today we have Professor Ram Gopal Rao, Director, Indian Institute of Technology, Delhi, for a much awaited lecture in this lecture series. We also have Professor Gurvinder Singh Virk, Dean of School of Engineering, UPES, and I am Dr. Devesh Avasthi, Dean R&D at University of Petroleum and Energy Studies. I would like to give a short background. UPES initiated a science series consisting of 6 lectures by renowned scientists of India and abroad, especially for school students and teachers. The activity is in association with Institute of Physics UK, Indian Physics Association, and Indian Association of Physics Teachers. I am sure the students and teachers will enjoy this lecture series. You will be glad to know that all those who attend 4 out of 6 lectures will be given e-certificate for participation in this event. There will be a quiz at the end of lectures on 7th of August, actually at the end of lecture series on 7th August, which will be based on the questions from lectures and school level knowledge. 2 quizzes are planned separately. One quiz is for school students and the other is for teachers. The students and teachers attending the lectures are welcome to participate in the quiz on 7th August. The prizes for both quiz are sponsored by Indian Physics Association and Institute of Physics UK. Today is the second lecture of the series by Professor Ram Gopal Rao, Director IIT Delhi, a renowned technologist and engineer of international fame. I owe a special thanks to Professor Rao to spare his valuable time for students. Now I would like to request my colleague, Professor Gurvinder Singh Virk, Dean, School of Engineering, UPS, to welcome the speaker. But let me first briefly introduce Professor Virk. Professor Gurvinder Singh Virk holds a PhD in control theory from Imperial College, London, and has held 15 professorship positions in 7 countries, UK, France, Sweden, New Zealand, Germany, etc. He has worked in robotics for for 25 years and is also managing director of a Endo Energy System, which is a company commercializing wearable assistive exoskeletons located in Mohali, Punjab. At UPS, he has started a major research and engineering initiative via 4 flagship projects: flying cars, smart cities, disaster management, rural technology, all focusing on advanced engineering. So with these words, now over to Professor Vic.
Thank you, Professor Avasti. It really gives me great pleasure to introduce our speaker for today on the topic of nanoelectronics. Professor Rao, as Professor Avasti has said, is currently the director at IIT since 2016. He has an incredible CV, and I will just be able to give you a snapshot of the things he's done. Otherwise, he will have no time for his talk. So, but even those things, I think will give you an idea of the man who is going to tell us the nanoelectronics field. Before joining IIT Delhi, he was at IIT Bombay, where he was the PK Kelkar Chair and Professor of Nanotechnology in the Department of Electrical Engineering, and also the Chief Investigator of the Center of Excellence in Nanoelectronics. So clearly, he knows the nanoelectronics field inside out, and which is also shown by his prolific publications. 475 publications to date, probably has surpassed that, and also 48 patents, which is also very, very impressive, of which 8 have been issued by the United States. And not only that, but 13 of these patents are actually being used by companies, which is also impressive. So many of us write patents and they go nowhere. So, sir, well done. This is a really, really impressive record. And he has also been founder or co-founder of two startups at IIT Bombay. And I'm sure he's probably going to do the same at IIT Delhi in due course. The name of the startups give you an idea: NanoSniff, so clearly sensors, and the soil sensor, SolSense, looking at sensing various properties of soil. He has been very active in terms of his contributions to engineering. He's a fellow of most of the professional organizations, including the IEEE, the Indian National Academy of Engineering, the Indian Academy of Sciences, fellow of the National Academy of Sciences, and also the Indian National Science Academy. So all these work has not gone unnoticed, and he has had numerous awards, in fact 30 awards from our own country as well as abroad. And he also has had 3 honorary doctorates and many, many other prizes. He is editor of, was the editor of the IEEE Transactions on Electronic Devices for around 12 years, from 2003 to 2012, and even now sits on the editorial advisory board of the ACS Nano Letters Journal. And of course, a very distinguished lecturer. So he's been recognized as a distinguished lecturer by the IEEE Electronic Devices Society. So with those words, we really are looking forward to your lecture, sir. So over to you. Thank you.
Thank you very much, Professor Vark. Thank you, Professor Awasthi. I would like to thank UPES for inviting me for this talk. I'm very happy to be speaking with students. Today's 11th and 12th standard students are our future engineering students. I'm sure all of you are aspiring to, come to our institutions. But in India now, there are also some excellent science institutions. If you want to pursue science, of course, there are great universities like UPES, but there are also IISERs, the Indian Institute of Science, Education and Research, which are as good as IITs, but they focus mostly on the science-related subjects. So I think India now offers enormous opportunities for pursuing quality higher education. So my talk today, I will talk a little bit about my primary area of research, which is nanoelectronics. And I will be speaking in general about what nanoelectronics is and where are we headed right now and what is happening. And I will use mobile phone as an example, as a platform to tell you what exactly is nanoelectronics doing and where are we headed when it comes to the mobile phone technologies and what has happened and why is it happening, meaning how is it happening. So the how part of it is also something I will touch upon. This is also, these contents, in fact, most of these slides I have taken from the first lecture I usually give to students in IIT, the first year BTech students, the first lecture. So these are all the contents that I have, I used to teach this course for a long time, and so I've picked up these contents from there. Of course, I have updated in the recent past. If you look at the mobile phone, just look at this decade 1994 to 2004. That is when the mobile phone revolution really, happened. And the first mobile phone looked like this in 94 from Motorola. And then they started to shrink the mobile phones smaller and smaller. And by 2004, you started to have something called a smartphone, and you were able to do things beyond just calling kind of a thing. The initial generation of mobile phones were primarily designed for voice calling, and they were not able to do anything other than that effectively. But slowly, these mobile phones became smartphones. And if you see the current 2021, I mean, you are talking of foldable phones and phones becoming tablets when you open them, and you can pretty much do all your work on a phone now. For example, I use laptops only when I need to give talks now, or when I need to present or prepare some word files, long large word files or PowerPoint presentations, unless I'm creating something which is like a multimedia kind of a thing, I hardly use my laptop anymore. All my for my email and other things, I mostly do it on my smartphone itself. So phones have become, as powerful as what the laptops are. And the only problem so far has been the screen size. But thanks to these foldable kind of phones, even the screen size problem is going to go away, because you want smaller gadgets, but for readability point of view, you want the screen to unfold or become larger when you want it. And that's precisely what these folding phones do. And therefore, I think in the future, probably a phone and a laptop and tablet all will be one. You don't need to have one phone, one tablet, one laptop. I think many of these things will go away when you need to create some content to attach a keyboard, and then you are done. So that will happen very soon. In fact, by the time you start using these phones for your work kind of purposes, all of that will be a reality, because even in 21 we are seeing phones like this now. So having said that, but what has really made this revolution possible? I mean, from a consumer point of view, this is what has happened. But what is the technology behind that has really enabled applications of this nature? Now, if you even see the memory capacities, the memory that you can buy today in the market on a chip, in 2004, in this form factor, you were able to get a 128 MB kind of a memory. And today in the same form factor, you can get 1 terabytes of memory. So that's a huge amount of memory in the same die. So in the same area, what is that you have been able to do, that you have been able to increase from 128 megabytes to 1 terabytes of information? And the 1 terabytes is like, you can store 2000 movies on this, even in high quality kind of a format. So I think that is what the technology has become. And what we are going to look at in the next half an hour is what has really made all of this possible. What are the technologies behind this sort of a revolution that we have seen, from a science point of view, from a technology point of view. If you look at the mobile phones, what is that you expect out of these mobile phones? If I am buying a mobile phone, and if I 5 years from now, what are my expectations out of this mobile phone? If you look at the complexity that goes into a mobile phone, it's almost tending towards infinity. The mobile phones are probably the most complex gadgets, because in that form factor, to be able to do all that you do today with a smartphone, and using the batteries that you have in those phones, you need to have from 128 megabytes to 1 terabytes. That is all tending towards the infinity kind of a thing. And then when you look at the delay, you want these mobile phones to be faster and faster. So these days nobody has. If it takes a few hundreds of milliseconds, you start to worry. You start to get irritated. You want everything in a flash, and now everything will just happen without you even blinking your eyelids. So I think you are expecting the delays to become zero. And nobody has any patience to wait for data downloads. And all of that needs to become faster and faster. And then the power. You also want your battery life to be forever. I mean, you don't want to charge your battery, and you don't want to you want your battery to last forever. And so therefore the power consumption from the phone should be zero. I think the phone should not consume any energy, but at the same time should be faster and should do many more things than what you really wanted to do. And you also don't want to pay any price for it. And if at the end of the day you want all of that, without having to pay some huge amount of money for owning these gadgets. You want it to be cheaper and cheaper. And in fact, the joke is, if somebody says I will give you when the price becomes zero, if somebody says I will give you one, you start negotiating, why can't you give me two, kind of a thing. So therefore I think that you are expecting the cost to go down to zero. And with all the performance improvements, with all the increase in the complexity, you still want the cost to go to zero. And then every year or every 2 years, you want a new gadget. If you are given a mobile phone, just imagine after 3 years, you start feeling restless. You start feeling that there is a better phone in the market, and you want to buy that, but you want it to be cheaper. You want that new phone to last longer in terms of battery life. You want it to do many more things than the phone that you own right now. So, but all of this you want in a design, from a designer point of view, from an engineer point of view. If I have put out a phone today, 2 years from now, I know that my customers are expecting, something better, something grander, something, which is more powerful. All of that in 2 years time, you need to redesign the entire thing and be able to, put that into the market that is better than what you had put out just 2 years ago. So from a company point of view, from the engineers working in the company point of view, you can see the pressure that they all go through, in order to achieve this sort of a improvement, every 2 years kind of a timeline. So typically every 2 years you expect, some major improvement in whatever gadget that you have bought. And at the same time, you want the sizes to be smaller and smaller. The size and complexity, of course, go hand in hand. As you start shrinking the sizes, because you don't want to carry a very bulky kind of a phone. You want to carry something which is very smart, very cute, very neat, and very fast, and long battery and all of that. And but at the same time, you want all of that to happen in every 2-3 years kind of a time frame. So therefore, these are the expectations that we have, come to think about. I mean, if you look at it, these have become, we have just these are the way we expect things to become every 2-3 years kind of a time frame. So now, if you look at it from the other side, these are the expectations as a consumer, as somebody who is buying these gadgets. But from an engineer point of view, or from somebody who is now, working on these technologies, what would be the pressure on them? How can they keep on, putting out the better and better technologies every 2 years? So let us see, how exactly that happens. So now, if you look at any mobile phone or any of these gadgets, the major part of the phone is going to be the chips, the integrated circuits. And these integrated circuits, as you all know, you would have all seen those integrated circuits. They're all the digital circuits, the logic, the microprocessors, for example, the Intel Pentium processors or AMD processors. All these processors are basically, these are all the microprocessors. They can, deal with these ones and zeros, the digital logic very well. And there are 1 billion transistors now on a die. And in 1 millimeter square silicon area, silicon is still the most widely used material for all of these applications. In 1 millimeter square silicon area, today you can put 1 crore components. 10 million components in 1 millimeter square silicon area. So that is the kind of a complexity that we have been able to achieve. And using all these components, you basically do a lot of logic operations, your additions, multiplexing, and all of these AND gates, NAND gates, NOR gates. There are billions of such gates now inside these chips. And so using that, you perform all the logic operations. And then, you somehow you have also some analog circuitry there, because analog is the one through which you interface with the external world. But at the end of the day, all the processing is done digitally by converting this analog to the digital formats and doing the processing. And then for consumption purposes for humans, now you again convert it back to analog. And so therefore there are A to D converters, analog to digital converters, digital to analog converters, but all the processing is done in the digital kind of a format. So therefore, when you think of microprocessors, you think of logic. The microprocessors are full of those logic elements. And many of you, I am sure, have already done these digital logics, the AND gates, the OR gates, the NOR gates, all of these gates. Basically, what are these gates? A few bunch of switches. So if you give me switches, I can connect them in parallel or series, and I can eventually achieve any kind of a logic operation that you want me to do. So if you treat this as a bulb, so if you treat it as a bulb here, so now if you have a gate, if you put 2 gates in series, and when these 2 gates are closed, and if you apply a voltage here, now the bulb will glow, because both the gates, whether this and this are closed, therefore the bulb will glow. Now if you connect the 2 gates in parallel, right, if either if this is open or this is open, the bulb will glow here. So therefore you can also have AND gates or OR operation kind of a thing. So even if one of them is open, and now this bulb will glow here. Both of these, one of them is closed, the bulb will glow here. Here, both the gates need to be closed. And similarly, so therefore, if both of them are open, now the bulb will not glow. If both of them are open, the bulb will not glow. So therefore, all these logic operations you must have done, the AND gates, NAND gates, NOR gates, and all of that. Now, at the end of the day, the important thing here is the switch. So now keep in mind that the entire microelectronics, everything that you see inside the mobile phone, what is playing a role is essentially this switch. So if you can give me 1 billion switches, right, which are all interconnected, which I can connect the way I want them to, and to achieve my microprocessor operation, I can design a microprocessor, and I can give you all of this processing power on a mobile phone or in a handheld kind of a format. So therefore, at the end of the day, all that you are looking for is these these mechanical switches, the switches which are able to essentially give you the kind of a logic operation which make the logic operation possible, and so this is the switch that you want to essentially realize. Now, how do I realize the switch? I can use mechanical switches, but mechanical switches are very bulky, right? If I put, if I contact two electrodes, of course it's a closed switch. If I open the contact, then it becomes a open switch. So I can use those switches, but like I said, today in the silicon, when you make these switches, you can make something like in 1 millimeter square silicon area, I can do now one thing like 1 crore of those switches. 10 million switches I can do in 1 millimeter square silicon area using this material silicon. Now show me a mechanical switch which can actually perform that kind of a function, which can perform that function, but you cannot connect 1 billion such transistors together, to be able to perform any kind of an operation. Therefore, it's not possible to do that using such mechanical switches. So you need to look for an electronic equivalent of that. And you not only need to look for an electronic equivalent of that, you should be able to keep these switches smaller and smaller, right, without losing its functionality, and be able to integrate 1 billion of these switches in that 1 centimeter by 1 centimeter kind of a die. So therefore, so what is the technology that you therefore need for doing that? So you are looking at making these kind of switches exactly like a mechanical switch, which will function like a mechanical switch, but I can make it so small, and I can connect these switches the way I want, so that I can perform all the logic operations that I will require, so that I can now deal with tons of data. And storage anyway, is again, you use similar kind of transistors for the storage, and you can do so many operations using that. So that switch is basically this MOSFET. So MOSFET is the one. This is what is known as the metal oxide semiconductor field effect transistor. So this M here stands for metal, and the O here stands for oxide, and the S here stands for semiconductor, and usually this is silicon, and then this is the field effect transistor. So this is the mechanical equivalent of the switch. All that this switch basically performs is you can use this electronic device to replace a kind of a mechanical sort of a switch. That is all what this switch basically does. There is nothing complex about this sort of a device, other than treating it like a mechanical switch. Now the question is, how do you how can we really see this functioning as a mechanical switch? So now just look at this structure. So it's not a, though it looks, when you first look at it, it looks like a slightly complicated structure, but you just look at it carefully for a few minutes. Once you absorb it, there is nothing very complex about it. So let's see what exactly is this. So this is what, as I said, what we call it the MOSFET. And all the revolutions that you are seeing in any electronic, the consumer electronics today, the reason for that is basically this MOSFET. If this MOSFET had it not been invented, which was done by Shockley, Breton, Bardeen in Bell Labs, nothing would have been possible of what you are seeing today as consumer electronics. So this is behind all the revolutions that are taking place in our mobile phone technology or any consumer electronic circuitry that you or technology that you see today. So how does it actually, how does this simple electronic device function like a mechanical switch? And why do I need this mechanical switch? As I told you, if I can have billions of these mechanical switches or billions of these switches, I can connect them the way I want and perform all the logic operations, because you have seen that for an OR gate, how you connect, for an AND gate, how you connect. These are all connecting these switches in series or in parallel. That is all what is there to the logic circuit. The Boolean algebra is all about dealing with these switches, connecting them in parallel or series to achieve whatever Boolean function that you want to achieve. So therefore, the switch is very critical to all the microelectronics, all the logic circuit operations, all the logic the circuitry that you build. Therefore, we have always been looking for these switches that you can realize in a small form, and and also in a form where you can interconnect a billion of them together. So that is the magnitude that you are talking about. Now let's look at how does this circuit actually work like a switch. Now you see two junctions here. Many of you, I understand, I am told, have studied about the PN junctions. So now you know PN junction. So you have a P-type semiconductor, right? And you have an N-type semiconductor, and these semiconductor, when you put P and N junctions together, you get what you call it as a diode, right? So this is a diode. Now in this circuit, forget about whatever is there on the top, so this part of the circuit, don't worry about it. Now just look at what is there here. You have a N plus junction, which is a N semiconductor, and this is the P-type semiconductor. So there is a P-type here. So there is a N plus P junction, right? And there is again P N plus junction. So therefore, what exactly does it have here? You have now an N-type junction, right? An N-type diode. So this is the N-type diode, right? So and then you have another junction here. So what exactly is this now? These are two back-to-back connected diodes. So you have two back-to-back connected diodes, between which are basically what are forming this transistor. So you have a N junction here, you have a P junction here, you have a N junction here. Now when you connect two back-to-back diodes together and you apply now a voltage across this, let's say I apply now a battery across this, what will happen? Now if I connect a back-to-back diode and put a voltage here, will any current flow through this through these back-to-back connected diodes? When I connect a positive bias here, this will get reverse bias. And when I connect negative here, this will get forward bias. So at any given point of time, whether you invert the battery terminals, make them negative or positive or negative, if one diode is conducting, the other diode will be off. So therefore, no current can flow this transistor to these back-to-back connected diodes, irrespective of whatever is the polarity of the battery that you connect between across these diodes. So that is the basic function. So in the normal case, this particular transistor is off. So therefore, now in the normal case, if I apply a voltage across these two junctions, there is no current that can flow here. So this switch is basically off right now. So no current can flow. So this is equivalent of the mechanical switch. So I apply a voltage, right? And these two electrodes are open. Therefore, if I'm applying a voltage here, no current can flow between these switches because there is a NPN diode, back-to-back connected diodes. If this junction is reverse bias, this junction is forward bias, or vice versa, in any case, no current can ever flow. So now, so therefore, this switch, when I fabricate it, if I apply a voltage and if I am measuring the current between these two N plus regions, so this is basically the contact. So this is the contact. This is the contact to the gate here, and this is the contact to the source here. So therefore, these regions, now we call them, this sources the electrons. This is the drain. It drains the electrons, and this is called the channel. These from the source, the electrons flow through this channel and reach the drain. But in the normal operation, when in this particular instance, no current can ever flow because you will always see one diode reverse bias, one diode turned off, while one diode will be on. So irrespective of whatever polarity that you connect. So therefore, how do you turn it on? Now, if I want to turn it on, I want to be able to bring these two contacts together. I want to be able to close the junction so that when I apply a voltage, the switch will now become closed. When the switch becomes closed here, then I can switch this switch on and off. I can open the switch or I can close the switch depending on by applying a voltage. So that is the mechanical equivalent of a switch. So therefore now I can, by application of a tiny bit of voltage, 0.8 volts, 0.4 volts, I can now close the switch. If I apply a different kind of a voltage, I will open the switch. So I can now electrostatically control the on and off operation of this switch. So that is now a good thing. So now I have a switch which I can start controlling. Now the question is, how do I ensure that? How do I turn on this transistor? How do I turn on this device? Now, so we have seen that in the normal operation, the switch is closed. Now remember, this is the p-type silicon, right? So this is the p-type semiconductor. This is the p-type silicon. Now you are applying a positive voltage here. This is the gate. So now you apply a positive voltage. So what is the voltage you are applying now? Remember, there is a metal. So like I said, there is a metal here. There is an oxide, right? This is the, so treat this as the metal. So this is the metal. There is an oxide and there is a semiconductor, right? So now what do you have here? You have a metal, you have an oxide, you have a semiconductor. What exactly is the structure that forms a capacitor, right? So you have a parallel plate, an oxide is the one which acts as a capacitance, and then you have two electrodes. One electrode is a metal, the other electrode is a semiconductor. So therefore you have a parallel plate capacitor here. Now when this is a p-type semiconductor. So therefore when I apply a positive voltage to this, right? When I apply a positive voltage to this, what will happen to the structure? Now it will attract electrons, right? It will attract electrons to the surface because I'm applying a positive voltage. The electrons will come to the surface, and therefore what we call at the surface of the semiconductor, an inversion will take place. So we say that now there is an inversion that has taken place here. So now that is inverted, meaning the p-type semiconductor at the surface has become n-type. Why did it become n-type? Because by applying a positive voltage here, you are pulling electrons to the surface, and in this case there are huge number of electrons here. Therefore many of these electrons will flow to the surface, and as a result now you have n plus silicon, you have n-type semiconductor at the surface. This has become n-type, and you have n plus here. Now what has happened? Now those junctions have vanished. Earlier we had a PN junction which were back to back connected. Earlier we had a kind of a, you had the N semiconductor, P semiconductor. So you had this kind of a structure. Now this P region which you had here, now by applying a voltage, you have converted that into an N region. So when the moment you convert this into an N region, now you have lost the diode. So now there is no diode there. So now you have basically one slab which is N plus, which is what we are calling source. Then you have another N region which you have got inverted by applying the voltage, and then you have another N plus region which has basically become your drain. So now this is the channel. So this is part is the channel. This part is the channel. So you have source, you have drain, and then you have the channel. So therefore now it is basically one single slab of semiconductor N-type. And now if I apply a voltage across it, right? If I connect a battery across this, now the current will flow because it's just like a resistor or any kind of a piece of a semiconductor where if the more voltage I apply, the more current will flow. So therefore now you have turned on the transistor. So in the normal operation without any voltage, there was no current. Even if I connected, so therefore you have three terminals here. Remember there is a gate. So we call this the gate, we call this the source, and we call this the drain. Right? So now in the normal operation between the source and drain, whatever voltage I may apply, if I keep my gate voltage equal to 0, right? When my gate voltage is equal to 0, between the source and drain, I may apply any amount of voltage between the source and drain, but that source and drain will actually not lead to anything. There will be no current flow between the, let me show you this. So therefore, let me just draw it, in a simple fashion for you. So now what have we seen so far? You have a source region, right? And this is N plus, this is the N-type semiconductor, and you have a P-type semiconductor, right? And you have put another drain region here, right? So this is drain is also another N plus N-type semiconductor. And then you now have, this is entire thing is a semiconductor. So this is the P-type, right? And then you have through a gate and through a metal, right? And now you have started to apply a gate voltage. So this is your gate, this is your source, and this is your drain, right? This is the structure, which I have shown you before. Now, if imagine gate voltage is 0, right? And I apply a voltage between the source and drain. You apply voltage between source and drain. What will be the current that will flow here when the gate voltage is 0? No current can flow because basically the structure equivalent is you will see a sort of a back-to-back connected diode. So because there are two junctions, which are back-to-back connected, no current will flow when the gate voltage is 0. Now, what have we done here? Now, all that we have done is now we have started to apply a gate voltage. So now instead of 0 volts, let us say I apply 1 volt here. So instead of 0 volt, I apply 1 volt here. When I apply 1 volt, what will happen? This is a p-type semiconductor earlier. Now there will be inversion that will happen at the surface. This region will actually become N plus because it will attract all the electrons, from everywhere. And so therefore, when it will attract electrons, now the surface will get inverted. So then you will have N plus silicon, N plus channel, N plus drain, and it will eventually look like just one slab of semiconductor. And therefore apply a voltage. And since entire thing is N plus now, a huge amount of current will flow through the source and drain region. So that is a switch. So at the end of the day now, you have a switch, and this I can now control by a gate voltage VG. And this is what I call the source. This is what I call the drain. When you apply gate voltage VG above, you need to get sufficient number of electrons here. So when I get a gate voltage VG above some threshold voltage, now the switch will be closed. The switch will be closed. When I apply a gate voltage VG less than some threshold voltage, the switch will be open. So therefore, I can now get an equivalent of a mechanical switch in the form of an electronic switch, right? And I can open and close this switch with the help of a small gate terminal, and which is capacitively, inducing the charges in the channel. So with the help of a small gate voltage, I can switch a large current between the source and drain. That is the beauty of the MOSFET. And this is known as the field effect because there is a capacitive action there. The reason why you got the surface inverted is because of the gate voltage that you've applied. By applying a positive voltage here in a p-type semiconductor, you get the electrons to the surface, and therefore the current will conduct. And so by applying it with the help of a small gate terminal, I can control a large current between the source and drain. And that is the nice part of the transistor operation. And that is the reason why the electronics, all those Boolean functions, many of these where you have seen these kind of switches. Now I can do these switches by just using simple transistors now. So this particular device is known as the transistor, and the technical name for this is the MOSFET. Why is it called MOSFET? Because remember, as I told you, this structure, if you actually see this structure, there is a gate operation. The gate is basically capacitively coupled. So now why is it called a MOSFET? Because you have a semiconductor. So you have the semiconductor, which is this is a semiconductor, right? And then you have an oxide. You have the oxide, and then you have the metal, right? So metal oxide semiconductor, and this is N plus. The semiconductor will be of opposite type, and this will be N plus. And so this is the transistor. And so this is known as MOS. MOS standing for metal oxide semiconductor. And it is a field effect transistor. Why is it a field effect transistor? Because by applying a gate voltage, I am inducing a field through the oxide. There is an oxide here. There is no current that is flowing. When I apply a voltage, there will be a field across this oxide. What will be the field across this oxide? If this is considered a metal, this is considered a metal, highly conducting, all the voltage that you apply will basically drop across this oxide, which is an insulator. And the field across this oxide will be whatever the voltage that you apply divided by the thickness of this oxide. Whatever is the oxide thickness Tox, so Vg by Tox will be the field across the oxide. The more voltage I apply, the thinner I make this oxide, the higher will be the field. And the higher is the field, there will be more electrons now coming to the surface. If you apply more and more gate voltage, there will be more and more electrons in the channel region. The inversion will be stronger and stronger. So that is the reason why it is known as the field effect transistor. And so it is changing the transistor is transfer of resistance. Why is it a transfer of resistance? Earlier, as you can see, the switch was open. When I did not apply any gate voltage, when my VG was equal to 0, whatever voltage I apply between source and drain, it did not matter because no current was able to flow when my gate voltage was 0. The moment I applied a little bit of gate voltage, this inversion took place. When the inversion took place, the switch got closed, and when I apply a voltage, now a huge amount of current can flow. Therefore, you have a transfer of resistance from a high resistance to low resistance. You can transfer this resistance. That is why the name it is known as transistor. And the MOSFET is the device. So inside every integrated circuit you see today, 90% of those integrated circuits will use a transistor which looks like this. And that particular transistor is basically this. This is driving your entire semiconductor industry. This one single device is making all your mobile phones become faster, your computers to become faster, and consuming lesser energy, longer battery life. Every advance you have seen in any electronic device that you have ever used, this is the device which is behind all of those advances. So now we have only seen so far that how I can now use an electronic switch. The MOSFET is basically an electronic switch. Now I have so far shown you how with the help of a gate voltage, I can control the current between the source and drain. Therefore, I can now make this switch open or close by applying a small gate voltage using that capacitive, that field effect kind of an effect I can use to control the switch between on and off state and ensure a large current to flow between the source and drain. So this is something that I have shown. So a MOSFET is equivalent to a mechanical switch. So that is all what you need to know. And for us who work in these areas, do research in these areas, so we basically work on this device. How do you make it better and better? Now, if I give you a mechanical switch, I tell you two mechanical switches. I give you one switch here. I give you another switch, right? Made using by somebody else. Somebody has made a switch in one part of the world. Another person has made a switch in another part of the world. Now I ask you, tell me which is a better switch. Now, which is a better switch? The better switch is, if I am applying a voltage, right? If I am applying a voltage between these two ends, when the switch is open, what do you expect the current to be here? I expect the current here to be equal to off, right? The zero current, right? So what should be when the switch is open? I want my off current to be equal to 0. I don't want any current to flow when the switch is open. Now, what is when the switch is closed, right? I apply now, but I'm able to control the switch here, and I apply some gate voltage and I close the switch, right? When the switch is closed, what is the current that I expect out of this, the on current? I want the on current to be infinity. Because when the switch is closed, I want it to offer zero resistance. When the switch is open, I want it to offer infinite resistance. Therefore, one major characteristic of a switch is on-off ratio. I-on, the current that flows in the on state, to the current that flows in the off state. So therefore, I-on by I-off. What should be the I-on by I-off? I-on by I-off should be infinity. I want it to be zero resistance, therefore infinite on current, zero off current. Therefore, I want on-off ratio to be infinity as high as possible in an ideal kind of a switch. Now, if I give you one switch from one industry, another switch from another industry, I ask you which is a better switch between these two. You basically look for, you apply a voltage to the gate, you close the switch, find out how much is the on current, you open the gate voltage, turn off the switch, you find out how much is the off current, and you tell me that the on-off ratio is, let us say, 10 power 5 or 10 power 6 or 10 power 7. So whichever gives me higher on-off ratio, that is supposed to be a better switch. So therefore, if I give you a switch, and if I tell you what is the better switch between these two switches that I've given you, you will only characterize for the on current, you characterize for the off current, meaning on current when the switch is closed, off current when the switch is open. You tell me that this has a higher on-off ratio, therefore this is a better switch. That is all what is there as a most important parameter for any such kind of switches. So now, so far we have seen what it takes to really build a good switch. A good switch is the one which has higher on-off ratio. The higher the on-off ratio, the better the particular switch characteristics are going to be. Now the question that you need to ask is, a but when the switch is closed, right, when the switch is closed here, why is there a current flowing? The current should be zero. In a mechanical switch, for example, if I, even in my, in the homes, when you press a switch and all that, when the switch is closed, right, or when the switch is open, if you are not turned on the light, there will be no light, right? So therefore, that is because the mechanically there is actually no contact. Therefore, the current flowing between here is zero. But remember, this is not a mechanical switch. We are making it equivalent to a mechanical switch, but this is an electronic device. There is a direct connection between the source and drain. The source which is supplying electrons, the drain which is collecting these electrons. The channel is not a mechanically isolated. The channel is also a piece of semiconductor. It happens to be a p-type semiconductor. And unfortunately, there are no ideal junctions. In an ideal PN junction, in the reverse bias, the current should be zero. But but if I get if I look for a good micrometer, digital micrometer, and measure the current, even when it is supposed to be off, there will be a little bit of leakage current that is flowing between the switches. Therefore, even when I am not applying a gate voltage, despite it being two back-to-back connected diodes, despite this being two back-to-back connected diodes, there will still be some amount of current flowing, but that current will be picoamperes, femtoamperes kind of a current, depending on how you fabricate this device. But the moment you apply a gate voltage, VG, right, above some threshold voltage, then there will be a huge amount of current flowing. But when I say huge amount of current, how huge? Because there is these are not superconductors. These are not materials with zero resistance. Even when the switch is closed, right, when the inversion has taken place here, there will still be some finite resistance. There will still be some finite amount of current flowing. Therefore, on current cannot theoretically be infinite, right? Off current cannot theoretically be zero. So when it is off, you expect the current to be zero, but it is never zero. When it is on, you expect the current to be infinity, but it is never infinity because there is a physical resistance that will come into play. So therefore, all the modern switches, you always will have an ion by I of ratio, which is never infinity, but as high as possible, 10 power 5, if you are able to get, then you have made a wonderful switch using a particular technology. So therefore, this is the switch now. Now but these are the same switches that were used, whether it was the mobile phone of Motorola here or the mobile phone of Motorola here. The same MOSFET is used in both of these kind of devices. Now, if both the devices have used the same MOSFETs, how come that this particular mobile phone has become so much better as compared to the mobile phone, the first generation of mobile phone, the basic switch, the basic device that is used to build this logic operations is all still the same MOSFET that I have talked about. So what has changed from here to here and what has changed from here to here? What has basically changed is the size of this switch. So that is where that is what you always, many of you must have heard this word Moore's law, right? So all that has happened is Gordon Moore, who was the founder of Intel, who actually started that company, Intel. And what Gordon Moore said was, he said, you have a switch now. It's great that you have found an electronic switch, an electronic device which can replace a mechanical switch. Your mechanical switch, is so bulky and you cannot connect it. You cannot fabricate it easily. It is excellent that now you have been able to replace this particular mechanical switch with a simple electronic device, and you are calling it a MOSFET. You have an N plus junction. You have an N plus junction. You have a P junction. You have put a small gate. Now, with the help of this gate voltage, you have now able to control the current between the source and drain. So it is perfect. So therefore, you have a VG, and you have source, and you have drain. So he said, that's great. So you have found this switch now, but with these switches are still, with this switch, I can make that first generation of mobile phone. Now I want to make this phone better and better. So how do I now make this phone better and better? So now to make it better and better, you have to be able to integrate. If I give you a certain area, right? Now in this particular chip, let's say this is 1 centimeter by 1 centimeter chip. Now in this device, I can put, let us say I can fabricate these transistors, which are like 100 transistors. So I have been able to fabricate 100 transistors. Now after 2 years, right? Now after 2 years, can I fabricate in the same chip, the same 1 centimeter by 1 centimeter, 200 transistors, can I double the component density? Let's say in about 2 years time, can I double the component density? Now after another 200 years, now in the same 1 centimeter by 1 centimeter chip, can I fabricate 400 transistors? And similarly, after some time, I want to have 800 transistors. Then I want to have 1600 transistors. So I want to double this component density every 2 to 3 years. If I can do that, if I am able to add more and more components, then I can, start to use these additional transistors that I have in the same area to give you more logic functions. Earlier, you were able to only make a phone call. Now I can give you video. I can now give you a calculator. I can give you, everything that you want in that memory, in that mobile phone. I can give you if you allow me, to actually double the components on this die every 2 years kind of a thing. Now, how do I double the components? Now, if I'm able to, these transistors, if I'm able to put 100 of them in this 1 centimeter by 1 centimeter, and if I want to double these components, to 200, what do I need to make? I need to basically reduce the size of this transistor. So if I can reduce the size of the transistor to half, right? If I can reduce the size of this transistor to half, then I can put 200. Now from here to here, if I can further reduce the size of transistors, I can put 400. If I can further reduce the size by half each transistor, I can give you 800. So the entire game therefore is, how do I, now that I have found a mechanical equivalent of switch with an electronic component, which I call MOSFET now, how do I keep making this MOSFET smaller and smaller? And so that was what everybody wanted, everybody was going after. And Gordon Moore came over in 1965. So what Gordon Moore basically said was, he came up with what he said, a Moore's law. So what is the Moore's law? It's not like Newton's law or anything. It is basically the scaling law. So he saw that, how do we double the component density? So he said, to double the component density, you follow this particular principle. So he laid down a few guidelines. He said, if you follow these guidelines, you will be able to double the component density by making the size of these switches smaller and smaller with every generation kind of a thing. And once that Moore's law came into picture, right? Then there was no looking back, because now you were able to keep on reducing the sizes by half every time, and you were able to do a lot more things on the die. So this is how these transistors, this one which I have shown you schematically here, the same transistor basically looks like this in real fabrication. This is how these modern transistors look like, and you build multi levels of interconnects and all that. It is a pretty complex kind of a thing. And so this is what I was explaining to you. So the source, drain, gate, and this is the inversion. And this is where the channel gets inverted. Once the channel is formed, then a current flows between this. When there is no channel formed, then there is no current that can flow between these two. And remember, there are multiple dimensions to this transistor now. And if I want to know what is my goal is to reduce the size of this transistor by half. So I want to reduce the size of this transistor by half. How do I reduce the size of this transistor by half? Now for that, there is a length. This is what we call the length of the gate, right? This is the length between the source and drain, and this is the width for the transistor. So there is a W, the width to the transistor, there is a length to the transistor. In a 1 centimeter by 1 centimeter die, right? Now if you tell me that I want to put I want to double the components, Now, how should I reduce the size of L and W? When I reduce L and W, everything else also gets scaled by the same factor. So I am scaling everything by the same factor. Just imagine for a moment that I reduce W by, I reduce W by 0.7. I reduce the size of W by 0.7. I reduce the size of L by 0.7, right? Choose a scaling factor 0.7. And when I scale W, the width of the transistor by 0.7, length of the transistor by 0.7, assume that I'm scaling all other parameters by the same factor. All other parameters meaning the size of every other parameter I am scaling by the same factor. Essentially what will happen is the entire transistor will shrink in dimension by a factor 0.7. Now what is the area of this gate now? How much the gate area will reduce? W multiplied by L, 0.7 multiplied by 0.7, and that will be 0.49. So that as you can see now will be 50% reduction. So therefore, if I can reduce the W by 0.7, length by 0.7, I can now reduce the size of this transistor by 50%, and therefore I can now double the component density on the die. Since my transistor size is now becoming half, I can now in the same 1 centimeter by 1 centimeter chip, if I was earlier able to do 100 transistors, now I can give you 200 transistors. From now, when I again do the same thing, from 200, I can go to 400, 400 to 800. So for the past almost like 30 years, industries every 2 years, they have been able to reduce the size of these gate dimensions by 0.7. That is the Moore's law. So what Moore's law basically does is shrink this transistor and you are fine. That's what Moore's law said. And then people started shrinking the transistors because, and then they started to see that, all the great things have happened. So therefore, now we have reached a situation. They were all micrometers and tens of micrometers earlier. Now, people have started to go down to 130 nanometers. This is the same transistor. Remember, this is source, this side is drain, this is the channel, and this is the gate. So therefore, it's the same transistor that I have been talking about. So this is in schematic. This is what it basically looks like. The same transistor. So now 130 nanometers was the channel length. Now you went to 90 nanometers, scale 130 by 0.7, you get 90 nanometers. Then they reduce the size to 0.7 nanometers. Now again scale it by 0.7. So now you go to 65 nanometers. So you have the 65 nanometers. Scale by 0.7, 45 nanometers. Scale by 0.7, 32 nanometers. Scale by 0.7, 22 nanometers. And then now you are at a stage, where you are talking of something like 11 nanometers. The modern technologies that you have in your mobile phones use 11 nanometers. In fact, Apple and then Samsung have announced that they will be using a 5 nanometer process. Now, how far down can you go? After 5 nanometers, what? We are reaching now the atoms. So by scaling this in this fashion, by following the Moore's law, you have reached a stage where you are now hitting the fundamental limits. The scaling cannot go on forever. When you are, at 10 micrometers, from 10 micrometers to go to 7 micrometers was one thing, which was all right. But now you are at a stage where you are 22 nanometers, and now from 22 you are going to 5 nanometers. Now you start counting the atoms inside your transistor between the source and drain. Now, this length is something like, let us say 12 nanometers. Now 12 nanometers, there are just a few atoms separating your source and drain. You have one electrode here, you have another electrode here, right? This is one electrode, this is another electrode, and the distance between them is now just a few atoms, right? So now will this act like a switch? Now when I'm applying a voltage between these, right? Even if I am not applying any gate voltage, right? Will this actually act like a switch? When I have so few atoms, the current will basically tunnel through. You are bringing the two electrodes so close to each other, and you expect that a 10 nanometer channel, will basically stop the current between the source and drain, without the gate voltage, is too much to expect, because there is a physical connection there. These are not mechanical switches, where you have a physical kind of a open. So therefore, now people are hitting a limit where that ion by I off, right? The ion by I off, now that current is, that ratio is taking a major hit. On current is fine because you are bringing the electrodes closer. The on current, there is no issue, but the off current now is shooting up. Why is off current shooting up? Because now you brought these two electrodes, which are supposed to be physically separated, as close as 11 nanometers in distance. Therefore, your gate voltage is becoming less and less effective. Even if you don't apply gate voltage, with just the voltage between the source and drain, you are now seeing enough current flowing that the on current and off current are actually coming closer. And then you lost the MOSFET. Then you lost that switch operation. If you lose the switch operation, then there is no logic. Then you don't have a switch. If I don't have a switch, I cannot build any logic. If my on is the same as off, there is nothing that I can do with those useless switches. Then, so therefore, now that is a challenge that people are hitting. So now we have reached the fundamental limits of scaling, because the distance between the source and drain, the two electrodes which are supposed to be physically separated, now this gap has become, something like 10 nanometers kind of a thing. And at 10 nanometer distance, it's not able to offer enough resistance in the off state. So therefore, your switches are becoming leaky, and your mobile phone, even when it is not doing any function, right? You're not making a call, you're not doing anything significant, the mobile phone is still consuming battery, right? Your battery is down, you just turn on your mobile phone, don't do anything with this mobile phone, just leave it on, the battery is dead after some time. Why is it happening? It is happening because this switch, which is supposed to be open, is no longer open. It is actually conducting a bit of a current, because of the dimensions that we have reached now. So now industry is getting worried about it, and industry now, is looking for other alternatives. And now when you reach these atom level, when you start counting the atoms between the two electrodes here, then the physics changes, the classical physics breaks down, the quantum mechanical effects come in, and with all that, the understanding this device is now becoming so much more complex. And there is a lot of research that exists, many of us work on just understanding what happens when you have two electrodes separated by 10 nanometers. How do you model that current? How do you calculate that current? That is now becoming a very big challenge for industries. But one thing that has happened is, because the switches have become so tiny, in 1 centimeter by 1 centimeter die, now I can make a billion transistors easily. In any foundry you go, even a second rated foundry can give you a billion transistors, billion of these MOSFETs, integrated into this 1 centimeter by 1 centimeter die. So therefore the cost per transistor has come down. So now, as you can see here, the per transistor cost, that cost has come down drastically. So now we were talking of nano dollars kind of a thing, and the price per transistor is going down. The number of transistors goes up. So therefore, in the same die, now because you are able to now put billion transistors as compared to 1,000 transistors earlier. Now the cost per transistor, has now come down to a very small fraction. Therefore, your price is lower now. When you buy a mobile phone, the next generation mobile phone doesn't cost so much more than the previous generation mobile phone. Ideally, it should not, because the cost per transistor has come down, and because the number of transistors on the die has gone up. And but there is a technology cost that industries actually add to the total cost. If you want to buy an iPhone on the day it is launched, of course it is going to cost a lot of money. But you wait for a couple of years, once the technology costs are taken away, the actual manufacturing costs are not adding to the total cost. So therefore, at a lower price, you can buy better gadgets simply because of this Moore's law. So what Moore's law has done is, it has allowed you to put so many transistors in a die by shrinking the sizes, and as a result, the price per transistor has gone down. And now, because you now have so many billions of transistors available for you, the functionality has gone up. The mobile phone does so many more things than what you can normally do, and therefore it's affordable, and it does so many things better. So that is behind the Moore's law. But the question now is, how far can we go? So now, if you're talking of 5 nanometer processes, right? What more is left now? Is there enough room left beyond what we are doing right now? So industry now is worried. Industry is worried that what has helped us improve the performance because of Moore's law, the functionality because of Moore's law, it may not be possible in the future. Because now I have no headroom available to scale any further. When I was operating at tens of microns, it was easy. But when I'm operating at nanometers level, what can I go? How down can I go now from 5 nanometers? So now industry is very concerned about further scaling with the Moore's law. So now they are looking at alternatives. Now, some of the alternatives are the molecular electronics. This is an area where a Nobel Prize is waiting to be given. What people are saying is, when you are anyway going down in these physical dimensions for these transistors, why don't we use molecules? The molecules, anyway, the size of these molecules is a few angstroms, right? I mean, a nanometer could be an entire molecule. Can we use these molecules to switch? So whatever you were earlier doing with a MOSFET, by fabricating that MOSFET, can we find a molecule, which will switch on by application of some gate voltage, which will remain off when you remove the gate voltage. So with the help of a small gate voltage, can I now control the current between this electrode and this electrode? In between, I don't have a MOSFET. Instead, I have a molecule. And this molecular orientation, if I am able to achieve by applying this gate voltage, I orient it in such a way that it becomes an open circuit, and I orient it in another way that it becomes a closed circuit. So now, can I replace a MOSFET with a molecule? So molecular electronics is something which has become a very important area of research. If you want to know anything about molecular electronics in Nature Nanotechnology, last year there was an excellent review paper. The stability makes a difference. So the molecular electronics, the problem with these molecules is they work one day and they don't work the second day, and you don't know why it worked yesterday and why it is not working today. So because at the molecular level, understanding anything is pretty complex, and even to analyze molecules, you need supercomputers. If I want to start dealing with molecules, things become pretty complex in terms of physics. Things become pretty complex in terms of the computing. So as a result, it's bit of a challenge, but molecular electronics could be the future. And if you are able to do molecular electronics, compared to any transistor we have made, molecular electronics will be a million times smaller. So if imagine such molecular things, working the way you want them to work as a switch, can open up infinite possibilities, and the electronics will completely transform if we are able to achieve a molecule to perform the function of our existing MOSFETs. But that's a wide open area. Like I said, the Gordon Moore, the Shockley, Breton, Bardeen, who invented MOSFET, got the Nobel Prize, and that probably was the Nobel Prize that made the maximum impact to the humankind, because without electronics, nothing would have been possible. Now, the one who can show that a molecular kind of a circuit can be made, will again get a Nobel Prize for that. And there's a lot of work happening all over, but nobody has found a solution to that. The challenge here is when you do molecules, I can make an OR gate with a molecule. People have even made OR gates, AND gates with a molecule. But to make an OR gate or an AND gate with molecules, I need to be able to connect these molecules. How do I connect the molecule? These guys are 5 angstrom in size. How do I connect these molecules? And how do I scale up? Whereas for MOSFETs, the problem is scaling down. How do I reduce the size of a MOSFET is one challenge. The scaling down is a problem with a MOSFET. For molecular electronics, they are so tiny to start with. You don't have to scale down anything. Here, the problem with the molecular electronics is scaling up. How do I scale up now? Or when I say scale up, how do I connect a billion or 100 such molecules to make a circuit? How do I connect a billion such molecules to make a microprocessor? So therefore, for molecular electronics, scaling up is a problem. For the MOSFET today, the scaling down is a problem. So these are fundamental challenges right now, which no Intel, no IBM, nobody ever has cracked. How do you scale down the MOSFET further? How do you scale up the molecular electronics further? Are completely open-ended questions, which your generation will need to address them, because I think people have run out of ideas. What more can I do below 5 nanometers is not known in the MOSFET case. How do I now make a circuit by connecting 100 such molecules together and make them work synchronously to do any logic function like AND gate, OR gate, or realize your Boolean algebra, is again a completely open-ended question which nobody has found answer. So these are open questions here, and but then as engineers, you cannot keep quiet, right? And if I have sold a mobile phone as an industry to somebody, and that person is expecting the next generation of mobile phone in another 2 years time, and now here I've hit a roadblock with the scaling, because I have already reached the fundamental limit with respect to scaling, and I'm not able to make this transistor any smaller any further. But my customer is expecting that I come up with something better 2 years from now. So what do you do in that case? That is where industry has come up with what a kind of there is a term that is coined, what one calls is more than more. Now in industry, usually people talk about this word now, more than more. So what more than more basically talks about is, the Moore is basically the Moore's law, right? So the Moore's law talked about, by reducing the dimensions of your transistor, you double the component density, therefore you keep on giving more functionality, and everybody was happy. But now that the Moore's law has reached a roadblock, you have reached the the 5 nanometer kind of a limit, and you cannot bring the source and drain, the two electrodes, any closer. If I bring them any closer, it will not work like a switch. So therefore, I have hit a roadblock there. So therefore, Moore's law is not able to take us any further on the improvement path. So therefore, now industry has come up with this term more than more. What is more than more? In the more than more era, what one is saying is, I will not shrink my transistors. If I have a billion transistors, I will keep them as billion transistors. I will not, I won't be able to increase that any further without increasing the die size, but I will add other sensors here. So now in the more than more era, you are now trying to add sensors to the same die or to the same package, to the same system by adding more and more sensors. So therefore, you are talking of sensors plus all the logic operations which you were able to perform. Thanks to the Moore's law, this logic operations only became better and better, more transistors, so you could do many more things. But now can I add more and more? Because then this has now hit a roadblock. So can I add more and more sensors to my chip, to my gadget, so that now I can give you more functionality. Now can I sell you a mobile phone that will do diabetic monitoring? Can I sell you a mobile phone that will do blood oxygen monitoring? Can I sell you a mobile phone that will have the heart rate, the ECG? That is what the industries are beginning to do now. And that area, the more than more area, all the sensors part that you do is what we call the Internet of Things. Internet of Things is the network of physical objects or things embedded with their electronic sensors, power source. So you basically, have a tiny IoT kind of a node, and these IoT nodes perform different functions. This IoT can do ECG for you, or it can do the air quality monitoring for you. So your mobile phones now are getting enriched with these IoT devices. And now people are already talking of the IoT devices hitting trillion kind of sensor visions. They are saying that in a year, the number of these sensors sold will reach almost like 1 trillion, because you are not able to do anything much with the logic part of your circuitry as Moore's law has come to an end. Now you are trying to add more and more sensors, more and more variety of sensors, and then keep improving the performance of your mobile phone. If you look at the mobile phones now have so many sensors already. You look at any smartphone today, you already have so many sensors. And now to that, people are working on blood glucose, oxygen, blood pressure, heart rate, ECG, and anything that you can talk of. You want to add all of them, so that your mobile phone, will become attractive for you again. That after 2 or 3 years, you will buy a new phone. Because for a industry, if you don't change your phone, right, how will they sell more things and how will they grow? So they want you to buy new phones. But if the new generation of phone is same as what you are using currently, why would you buy that? And that is the situation we have reached now, because you are not able to follow the Moore's law anymore. I cannot give you a better quality or a better functional mobile phone than what you have already, because I'm not able to scale down these transistors anymore. Now the only way I can do that is by adding more and more sensors to whatever I already have, and in the process, excite you with that new gadget which can do more new things, and then you replace your phone and buy the new one. And if so many, if millions of people keep buying the new phones, the industry will grow, and everybody will be happy. There will be jobs. If industry grows, they will recruit people. When they recruit people, you will find jobs. So that is how the whole cycle actually works. So if you look at a mobile phone today, and compare it with the humans, compare it with yourself. You have 5 senses, right? You can see, right? And the mobile phones also can see very well. You can hear. Mobile phones also can hear very well. They have excellent microphones, and they have excellent cameras now. And you can touch and feel things. Mobile phones also can touch and feel things. They cannot feel, of course, but the touch sensitivity is there in almost every mobile phone. So 5 senses out of what humans have, the mobile phones have already captured them. The touch thing we do more effectively, but the mobile phones, use touch, but not as effectively as we do. But even that, with haptics and other technologies, even that is also for robotics now. All this is already, pretty very well advanced. So electronics is now able to capture 3 out of the 5 senses that you have. The 2 senses that your phone cannot do is it cannot smell things, it cannot taste things. So therefore, imagine a day a mobile phone can smell things. It can then do a lot of things. For example, if it can smell, we know the food quality by just smell. I just smell a food and I know whether the food is good or bad. You put something on your tongue and whether that particular quality is good or bad. So I think we do so many things with the smell and taste, and these are currently missing in your electronic gadgets, or particularly in a mobile phone. So therefore, can we start looking at electronic noses? So can we build electronic nose, and can we build electronic tongue? So this is the research right now which is happening everywhere. The future generation of phones might have that. Why do I need electronic nose? You know that for any airport you go, you have these sniffer dogs, right? Why are there sniffer dogs? Because they have a very high sensitivity for a smell. So therefore, they use sniffer dogs to sniff explosives, to sniff narcotics, and that is a gold standard. Any airport you go in any part of the world, the sniffer dogs are invariably present because there is no electronic gadget which can replace a sniffer dog. Now, a well-trained sniffer dog is like the gold standard for any sniffing kind of an operation. Can you build an electronic nose with the same sensitivity as a sniffer dog? And if I can do that, if I can integrate that into a mobile phone, now my mobile phone will become an explosive sensor. It will tell me what the other person is carrying who is sitting next to me, whether that person is carrying a bomb or whether the person is carrying anything which I should know. So I think that is what the future generation of these phones is going to be. But how do you enable these functions? That is where nanotechnology comes in handy. And nanotechnology is where which will allow you to build sensors. It can do many things, of course, but it will allow you to build these sensors which otherwise would not have been possible. And there is a lot of work happening now, using the nanotechnology. Since I have run out of time, I will maybe this is for some other day. But what we have basically done using nanotechnology is, we have been able to build these sniffer dogs. Now we have built an eNose. My group now, the company that I have started, NanoSniff, they actually build these eNoses, and they use again these tiny sensors, and it works on the same principle as the human nose. But this is a XSniff. This is like a sniffer dog, which is in a handheld kind of a format, and then we were able to reduce the size of this electronic nose into a small size. What we are looking at is, can in an airport, can you integrate airports with such sniffing devices, placed all over, and which are continuously tracking, the smell from the bags and other things. And when they detect anything, which should not have been there, it will warn the security people. So these are the kinds of security technologies that we are building right now. And but where do you want to place them? In fact, one of the projects that we are working on is, can you place such explosive detectors in the buses? When you put them here, when somebody walks into the bus carrying these materials, it will sniff like a sniffer dog. It will sniff that explosive and it will warn the driver. But this is a technology that we have, we are working on. But when you have such technologies, how do you power them? The powering these sensors, these are electronic devices, and a dog can eat and then do all of that. But electronic devices, you need to charge them. So how do you charge these electronic devices? And they are like mobile phones. Every day they need a charge. And you can use the power available in the buses. The buses already have that power. But then if you use that power, somebody will come, cut the wires, and then place the bomb and go away. So these devices need to be placed very discreetly underneath the seats and all of that. And for that, you cannot, do the complete wiring inside the bus. All that is going to be too much to expect from the deployment point of view. So one of the technologies we are working is in buses and trains, right? You have a lot of vibrations. When you are traveling in a bus and train, you have vibrations. Can we generate power from the vibrations? Can we generate energy from the vibrations and use that energy to actually charge the battery? So that is what is known as the piezoelectric sensing. So now you want to sense the vibrations and convert those vibrations into electric energy and use that electric energy to power the battery. So as long as the bus is running, the vibrations, the micro vibrations that the buses have or the trains have will become your source of power. And of course, in Taj Mahal kind of places, you can use solar and all of that. There is not a problem. For buses and trains, we are working on the piezoelectric energy harvesting to power the sensors. So this is a technology. And then so we have now a NanoSniff, the explosive trace detector is available. In fact, Honorable Minister of Education, Dr. Pokhriyal, recently launched this device commercially, and this nano sniffer, it can detect explosives in 10 seconds and all that. So therefore, this is my final slide. Small is big. So at the end of the day, we are now beginning to play with the atoms. When I say we are beginning to play with the atoms, now in nanotechnology, the biggest research area is, can you play with these atoms to develop materials for given applications? Meaning, I want a material with certain applications. Now, can I go and look at the molecular structure, arrange atoms in a particular molecular structure to give me those properties? Meaning, you are almost playing God. So you want to create now materials by arranging these atoms. So that is the power of nanotechnology. But for that, the science is what is important, and that science is currently missing. Today, what we all do is you take the existing materials in the periodic table, you keep on shrinking the dimensions of these materials, you bring the particle sizes to 5 nanometers, 4 nanometers, then you characterize what are the new properties the materials acquire at the nanoscale. That is nanotechnology. So therefore, using existing materials in the periodic table, synthesizing these materials in the nano form, 5 nanometers and below, 10 nanometers and below, studying the properties of these materials at the nanoscale because of the new physics that comes in is exciting science that many people are doing, and we already understand how materials undergo changes in properties at those length dimensions. Now the next step is, now once you understand all of that length, the dimensions and correlate it with the properties, now the question is, can you design materials for the properties that you require? And that we haven't reached because we still don't understand how these molecular structures will result in the kind of properties that you are looking for. But the engineers can play God if science provides them the tools, and that is what is missing right now. And I can assure you, all science fiction that you read today will be a reality tomorrow. That with a magic wand making things appear or disappear, that is all going to happen in the next 10 years. There is no science fiction anymore. So you just, your limit is what you can imagine. So all of that can be achieved in the next in this century itself. So all of that will become possible, making things appear, disappear, all that will happen. And I think my simple thing for you is become good at asking questions. I think answering questions Google will do. I think with AI, ML kind of technologies, any question you post to Google, Google will answer. But I think we need to be able to ask questions. This is one quality that will differentiate a good scientist from a bad scientist. So when you look at a mobile phone, you can be amused at what is there inside the mobile phone and do lots of things and all that. But you ask the question, what more this mobile phone can do? Can this mobile phone smell? Why can't this mobile phone smell? Once you ask that question, now you go on a journey of developing an electronic nose, and then you can really do wonderful things. So I think asking the right questions is what helps build the next generation of technologies. And in all of this, there is a lot of science behind, because science is the platform on which the engineering is built. If there is no science, it just becomes a jugaad kind of a thing. I think the real engineering happens only when there is a strong foundation of science. So I will stop here. Thank you very much.
Thank you, sir. Thank you, Professor Rao. It was a very interesting, very inspiring lecture. And this is something you introduced electronics at nanoscale in very simple manner. And you picked up example of mobile and its improvements in its functions over the years. How is it possible with the MOSFET and the working of the MOSFET, like switches and all such things. And yeah, so this is really inspiring for the students, and actually very thrilling lecture, I would say. Even I was actually learning quite a few things here. And Moore's law of increasing packing density every 2-3 years, problem going down at the 5 nanometer scale, dealing with the electric breakdown or atom level science. The opening interest in molecular electronics and their challenges therein. These are taking up to the current level challenges, and the later on, now you touched upon very interesting things of Internet of Things, where the sensors are clubbed with the mobiles for health monitoring and electronic nose, electronic tongue, and your company is doing those things. It is really thrilling and very exciting to know. And this also shows that there are a lot of challenges to the students, current generation, who have to take up these challenges in the coming years. So this is, I mean, I have no words to uh, express my thanks. It is, I am just speechless on this particular lecture. And I would now, with these words, I would like to take up some questions which students have asked. So I hope you allow for that. And these are, okay. MOSFET is present in which part of the phone?
Pardon? Yeah, I'm actually was reading the question. So
Yeah.
yeah, repeat what was saying. MOSFET.
Is present in which part of the phone? It is on the chips or this?
It's all
Yeah,
in the integrated circuits.
yeah,
The integrated circuits are all made of MOSFETs,
yeah.
and the silicon. 90% of the chips in the phones are all made with silicon. So silicon is the material that is used. I was
And
looking at this question. So, I mean, most of these questions, you will find answers in Google. I mean, I just look, what is advantage of MOSFET and what is VT? And so I
okay.
think I can see that, I can see that.
Okay, you can see the questions there also, right? Right. Yeah, 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 sure. Yeah, yeah. Okay. And I mean, there are very basic questions there are, and uh,
But
maybe some of them we can answer, and rest my team will actually respond to that.
for example, what is tunneling? And so
Yeah.
these are interesting questions. You know, my in I mean, for children 11th and 12th, you know, these are very advanced areas. We all spend our lifetime in working on these topics. So the idea is to generate curiosity.
Correct.
So now that the questions basically, you know, I can see that many people have become curious, and which is the good sign. And now I think one should work further to understand what this can be done. So what is nano tribology, and what is so what is ECG, what is CMOS image sensor? If we shrink our transistor up to 22 nanometer, then how can we improve failure rate of these components? I think these are good questions. You know, I can see that, but the basically, you know, the point here is at the heart of all the revolution that you have seen in consumer electronics lies that one single device. And so this particular device, MOSFET, you know, which is basically two back-to-back connected diodes, right, with a gate on top. That is such a simplest kind of a device one can imagine. But such a simple device has enabled a revolution in the consumer electronic space, and has made it possible whatever we see as advancements today. Now going forward, I think all the advances have come about because of the Moore's law. Basically, make this transistor smaller and smaller, and everything happened until now. But now the question is that you cannot do anymore. And
Yeah.
since you've reached the fundamental limits, so therefore now what are the new directions? One new direction is that more than more, where you add more and more sensors to the platforms and then make them more functional. That is one approach. The other approach is to fundamentally change the MOSFET, changing MOSFET to a molecular switch. And that, and like I said, is a Nobel Prize winning work. Multiple Nobel Prizes are awaiting there, because that MOSFET and IC got at least 5 Nobel Prizes. And so I think the molecular electronics can get many more Nobel Prizes, but that will be this century. So the this century will be all about finding those replacements for the molecular kind of switches. So
Yeah. Yeah, this is clear that it is basically all the game of bringing down the gate length from 130 nanometer to, let's say, now 11 and 5 nanometer and so, but that's the limit, and that's why we are stuck. And the key thing, as you say, is that now add additional features through sensors, so that people still remain interested in some additional features. and health monitoring, everybody is interested. So these are something very interesting. Health and safety. I mean, this explosive detection is something very much desirable in current scenario, not only in India, everywhere. And 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 this has its own challenges, that how to power it in different places. And you very nicely explained that how we can harvest the power from moving of the bus, vibrations and trains and all that. So these are very challenging areas to work on. And and I am sure that this kind of thing will motivate a lot of students to take up these challenges in the future to work on. So this is definitely a very, very inspiring for students. Yeah,
Thank you, Professor Awasthi. Thank you. I think I have taken a little bit more time than what was given to me, but
it's
I
okay, sir. Yeah, yes,
always
sir.
get carried away by these topics. But they are uh, so much, they are so interesting and so much exciting.
Yeah.
Thank you. Thank you.
I would like to personally invite you to campus whenever possible. You can see the beautiful background at my entrance place, and it will be, and the students therein also will enjoy interacting with you. I mean, I cannot convey such things which you can do with your own experience, and your company and our incubator center at UPS will also benefit in a big way. There are a lot of students who are actually creating their own startups at university and getting incubated. So it will be fantastic, sir. So I think we can stop interacting on in this, and I have some.
I will leave now. So thank you so much.
Yeah,
Thanks a lot.
yeah. Thank you, sir. Thank you.
Thank you very much. Thank
Yeah.
you.